Okay, so welcome to the session of today, the last of the week, and it's a pleasure to have Carlos Hoyos that will speak about effective action for anisotropic quantum Hall states. Please.
Okay, thank you, and thank you for to all the organizers for setting up this workshop. It's nice to be back in front of people. So I'm going to talk about this effective action for the anisotropic quantum Hall states because I think it was the topic that was fitting better with the theme of the workshop, and it's based on this paper with Fran Peña Benítez, Piotr Surobka, and Ruben Liar. Okay, so as usual, everything I say that is wrong is my fault and not my collaborators. So, okay, as you all know, quantum Hall transport is very much related to topological properties of states of matter. In particular, transport coefficients are determined by some of these topological properties of the state. And also, they can be described in an effective action using topological terms, in the sense that terms that do not depend on the metric. So the canonical example is the Hall conductivity described by the Chern-Simons-Gates field. Also, we have Hall viscosity that in the non-relativistic theory can be described by this Wensi term, where this omega is a spin connection. And you can also have like a Chern-Simons for the spin connection that describes Hall thermal conductivity. So the point of view I'm going to take for this effective theory description is that we start at the microscopic level with some lattice model. Then we look close to the Fermi energy to low energy excitations, and that can be described by some effective fermion model. And if these fermions are gapped, you can integrate them out, and then you go to the lowest level of the effective action. Now, usually, well, for simplicity, or in many cases, it can be a good approximation, we assume that the level of these low energy fermionic excitations, we have some rotational invariance. Okay, so this is the thing we are going to break here. We are going to break rotational invariance. This allows, in principle, more transport coefficients. And also, in principle, it will generate non-universal contributions to the transport coefficients we had before. Okay, so we want to study how this breaking of rotational invariance. And we're going to take a particular kind of model. So our laboratory to study this will be this so-called semi-dirac semi-metal. So because there is some people in high energy physics, let me explain a bit of the jargon. So first, in this plot, you can see the vertical axis is the energy, and the width of these areas at a given energy that corresponds to the number of states. So for instance, in an insulator, there is a gap in energy and there are no states. In a metal, there are many states at the Fermi energy. And then a semiconductor is a smaller gap than an insulator. And a semimetal is essentially a conductor, but where the number of states at the Fermi energy is very small. So we're going to be interested in this kind of semimetal state. And the canonical example is graphene. No, at least for me, that will be the canonical example. So in this case, you have an hexagonal lattice, and then in these corners of the Brillouin zone, you have at each of these points two physically inequivalent dirac cones. Okay, so you see that at the Fermi energy, no, this will represent the number of states. At the Fermi energy, you have essentially 0 states. So that's why it's a semi-metal. And each of these cones has some topological number associated to it, which is this that we call chirality, and each of the cones has a different value for this chirality. One is +1 and the other is -1. So this means that these cones are topologically protected by this Chern number. Now, this is just one example, but there are many classes of topological semimetals. Okay, so attending
sorry,
to,
if you include spin, there are 4.
sorry. There are 2 cones, no, but there are 4 bands because each of these. So this is considered one band. This is another band. This is another band, and this is another band. Okay, so this is 4.
Never mind. You consider spinless fermion. You consider spinless fermion or spin?
Yeah, I will consider spinless fermions.
Okay, so that's fine.
Okay. So there are many types of topological semimetals according to whether you just have a single point where the bands are touching, like these cones. You can also have lines. This will be these nodal lines. And you can be in 2 or 3 space dimensions. You can either have a twofold degeneracy. This will be like a bile cone in that is the label that is given to it. So each of the cones I saw is a bile cone. And if you just have a bile cone, you should have either parity or time reversal broken. Or you can have some 4-fold degeneracy, which will be called dirac. And in that case, you can have P and parity and time reversal unbroken. And another way to classify these nodal topological semimetals is whether these cones are localized at some particular point in the Brillouin zone, like a symmetric point, like in the previous case, or you can move them around. So in that case, they will be unpinned. Okay, so what we are going to consider is we have nodal. We're going to have only 2 components for the only 2 bands. So it will be in this label a bile semimetal. And we will consider that these positions of the position of the cone is not fixed around in the Brillouin zone. And to be more precise, it can move on a symmetric line. And I'm going to call it a Dirac semimetal because essentially we have 2 components of a fermion in 2 dimensions, so that in relativistic language, it will be a Dirac spinor. No? But in condensed matter language, it will be a bile spinor. Okay, so let me start with the effective action at the level of the fermions. This will be the simplest description of this kind of anisotropic semi-Dirac semimetal that I want to describe. Okay, so you start with this Hamiltonian. This will be like the usual kinetic term for a relativistic fermion in the x direction, but you're missing the contribution in the y direction. And instead of that, you have this term that depends on momentum and this parameter delta, which is an energy scale. Okay, so this can change sign, and you can have 3 different situations. If delta is negative, there is an energy gap, and you have an insulator. If delta is 0, these 2 bands come together and touch at a single point. This is the critical point. And then if delta is positive, then these bands touch at 2 points. Okay, so this will be the Dirac semimetal phase. Now, if you go at very low energies, you see that you will have 2 cones instead of just 1. But in this description, there are just 2 bands. Now, I'm interested in this critical point. This is the semi-Dirac semimetal. And one peculiar thing about this point is that the dispersion relation is anisotropic, and in such a way that in the x direction you have a linear dispersion relation, and in the y direction you have a quadratic dispersion relation. Okay. So notice that this point is topologically trivial in the sense that this chirality will be 0 because it will be the sum of a +1 and -1. Okay, and that's why it can be gapped simply by changing this delta. Okay, so in this sense, this is not protected topologically, this point. Now, the way to see this separation between the two while cones is that we move them along this momentum in the y direction. So this is the symmetry line I was talking before. Okay, so this kind of critical point may be realized in some kind of in some two-dimensional materials or in some kind of models. Okay, so apart from this toy model, you can also look at this kind of systems and find this kind of behavior. Now, let's look at the symmetry under time reversal and under parity. Okay, if I do a time reversal transformation of this Hamiltonian, I find that the ordinary relativistic kinetic term is invariant, but this other term that depends on the momentum in the y direction is changing sign. So time reversal is broken. And the same happens if I look at parity transformation, let's say in the y direction. The Dirac kinetic term is invariant, but this other term is not. But in both cases, the change is by a sign. So if I combine both transformations, the Hamiltonian is invariant. So this Hamiltonian is invariant under PT. Okay, and this will be a very important property of this Hamiltonian that we will use to constrain the effective action. Now, in order to gap completely the system, what we do is we introduce a magnetic field. So we will assume that there is a strong magnetic field. We have Landau levels, and we fill completely these Landau levels. So the state is gapped, okay, for all values of this parameter delta. Okay, so if delta is negative, as we were saying, there was already a gap, then the dispersion relation looks quadratic. This is like having non-relativistic fermions. So here we will have ordinary Landau levels. If delta is positive, we have these two Dirac cones, or these two bile cones. And then that will look at low energies like a relativistic system, and you'll have relativistic Landau levels. And then in between, you will have this semi-Dirac dispersion relation. You expect to have some kind of Landau levels, but in principle, their properties will be different than the Landau levels on both sides. So an implicit assumption we make is that if the magnetic field is much larger than this delta, then there will be a region above this critical point where you can still describe the system with this semi-Dirac dispersion relation. Okay. So if you want, this is kind of analogous to using temperature as the vertical axis and having a quantum critical point at 0 temperature. Okay. Now we want to write an effective theory for this region of B much larger than delta and study the anisotropic Hall transport with this effective theory. Now, before going to the effective theory, let's see what we know about the quantum Hall state in this semi-Dirac semimetal. Okay, I told you that Landau levels are not going to be the same as in either the relativistic or the non-relativistic fermions because the dispersion relations are different. Okay, so this was actually studied in a lattice model. The lattice model itself was introduced by Sato, Tobe, and Komoto. And it's essentially like this model I showed you before of graphene. changing the hopping parameter in these horizontal bonds. So the other bonds, the hopping will be 1, and the horizontal bonds, you can change it. So if T is 1, you just have the graphene I was showing you before. At T equals 2, you have the critical point where you have the semi-dirac behavior. And for T larger than 2, you have an insulator. So if you compute the energy of the Landau levels for each value of T, what you find is that at T smaller than 2, you have the relativistic dependence of the energies with magnetic field, which goes like a square root of the magnetic field. At T larger than 2, where you have an insulator, you have the ordinary dependence, which is that the energy grows linearly with the magnetic field. And in the critical point, in the semi-dirac point, you have this funny 2/3 scaling. Okay, but this exponent is actually easy to understand if you think about the scaling symmetry you have in the effective theory. So let's go through the argument. The magnetic field is going to be proportional to the product of the momentum in the x and the y direction. And in the relativistic case, the energy and both momenta are all have the same scaling. So the energy goes linearly with the momentum. So everything has the same scaling, and then it follows immediately that the energy will go like a square root of b. In the Galilean or non-relativistic case, the energy goes like the square of the momentum, and the two momenta scale in the same way. Okay, and then from here you can see that the energies will go like the magnetic field. And in the semi-Dirac point, the momentum in the x direction and the energy scale in the same way, but the momentum in the y direction does not. No? So the energy actually scales like momentum in the y direction square. So this means that this magnetic field will go like momentum in the x direction to the 3/2, and then from that you extract this 2/3 exponent. Okay, so it just follows from this kind of argument. So we expect that the energy of the Landau levels will have this kind of scaling and this exponent as long as magnetic field is much larger than delta. So as long as we are close enough to the quantum critical point. Okay, so after this piece of information, now we can go to construct the effective theory. Okay, so it's very useful to have a covariant formulation for the effective theory. Now we're going to integrate out all the fermions, so we will just have something that depends on sources, and it's useful to have it in a covariant way. So for the quantum Hall state, Son introduced this Newton-Cartan formalism, which is adapted to the symmetries of the usual quantum Hall system. Particularly if you have a clean system with Galilean invariance, is the perfect fit for that. Now we don't have any Galilean boost invariance, and we also have this special anisotropy. This doesn't mean that you cannot use Newton-Cartan. You can still use Newton-Cartan, add some more ingredients, and describe it, this system in a covariant way using Newton-Cartan. However, there is no intrinsic advantage of using Newton-Cartan because the kind of symmetries we have are completely different, are quite different from the usual quantum Hall. So what we will do is take Newton-Cartan as inspiration, but construct a different covariant formulation, which is more adapted to this problem. Okay. And something similar was also done by Copetti and Landsteiner, but in 3 dimensions. Now, so let's remember a little bit about Newton-Cartan. No? So the idea is you can take your spacetime, you slice spacetime in spatial hypersurfaces, and these hypersurfaces are determined by one form with components n mu. Okay, so this is one of the ingredients of the Newton-Cartan, and essentially this is telling you what is the direction of time. Then you add a complementary vector field with components v mu that satisfies this condition. And then you have the projectors on the space surfaces, which are these h minus. And morally, these are just the metric on the spatial slices. Now, in addition to these basic ingredients, you have to define a connection, which in the case of Newton-Cartan usually has some torsion. Now, because this involves V and N, this torsion is of time type, right? More than space-time. So we're not particularly interested in having this torsion or not. So this is not an ingredient we are going to require. Now, Galilean invariance implies some local symmetry, which are these Milne boosts that essentially shift the field V mu. So V mu you can think of as a velocity. Okay, and in particular in the quantum Hall, you can replace V mu by the Hall, the velocity that you obtain from the Hall current. So we don't have a Galilean invariance, so this is not going to play a role for us either. Okay, so in the absence of these two ingredients, we can just use frame fields to rewrite Newton-Cartan. So what's the idea of these frame fields? You have your spacetime, you pick one point in this spacetime, and then you pick a basis of vectors on this point, and you do that on every point in a spacetime. So you label each vector in the basis with an index A, and the components of each vector are these EA mu, which are these frame fields. Now you can also construct the dual basis, okay, that will satisfy this condition. And then if you have these frame fields and introduce a time-like vector, TA, which can be fixed, then this field of Newton-Cartan and mu that defines the time direction, you can see just as projecting the dual Vielbein on the time direction. And the vector V mu, you can see it as projecting the Vielbein on the time direction. Okay, so with the frame fields and this fixed time-like vector, you can recover these two fields of Newton-Cartan. And then from the metric, you can recover the projectors. Okay, so this is just two equivalent descriptions of the same thing. So what we will do is simply change this time-like vector by a space-like vector. Okay, so instead of having an anisotropy in time, we have an anisotropy in space. So we just need to change what kind of break-in we are introducing. Okay. So now with this idea in mind, let's go back to the fermionic action. Okay, so I'm going to write it in relativistic language, so in Lagrangian formulation. And we introduce the Dirac matrices, the two-component spinor, and the action of the Hamiltonian I was showing you before looks like this. So you have the usual kinetic term for the time and x1 direction. And you have this extra piece that looks like a mass that depends on derivatives. Now, the symmetries of this Lagrangian are, you have a Lorentz symmetry in the 0-1 plane, okay, which is an SO1,1 group. You have the particle number or the charge conservation, IU1. And you have also this global scale symmetry, where you scale the x0 and x1 with this lambda square, for instance, and the x2 with this lambda. So this anisotropic scaling. Now, concerning parity and time reversal, both are broken by this mass term. No? A mass term in 2 + 1 dimensions breaks both symmetries, but preserves p times t.
So, sorry, in the Lagrangian, the second term does not have any gamma matrix.
It has the psi bar, no? Is hidden a gamma 0. You're worried because when you go to the Hamiltonian, no? When you go to the Hamiltonian
So it's-
formulation, you have a
Psi is a,
gamma.
psi is a doublet.
Yes.
Psi is a doublet, okay?
Yes.
Okay. So that piece has identity in spinor indices. Okay. It's
They-
gamma zero, but
This is psi dagger gamma zero. Yeah.
okay. Okay.
Mhm. Yeah. Any other questions? Okay. So now let's try to make this look more covariant. So we introduce background vectors, LA with upper and lower indices, and a projector in the directions transverse to this vector. No, so here I'm picking L in the y direction, but you could pick L in any spatial direction. Now, with these vectors, we can rewrite this second derivative term in this form, no? Projecting the derivative with L. And the kinetic term, we can write it just contracting the projector with the gamma matrices and the derivative. Okay, so this will be the Lorentz covariant version. Okay, so this is covariant under 2+1 Lorentz transformations, but it's not invariant because L is breaking the Lorentz symmetry. Now, we want to go one step more, which is to introduce the background fields, preserving the covariance. So as I said, we have these Vielbeins and dual fields. And now we can define the projection on the L vector. So the projection in the anisotropic direction of these Vielbeins. So this L mu is the analog of N mu in Newton Cartan. And this L mu with upper index is the analog of V mu in Newton Cartan. And then these flat derivatives will become derivatives contracted with the Vielbeins. And in addition to the geometry, we introduced a background gauge field for the U1 symmetry. And in order to have a fully covariant action, we need to promote the partial derivatives of the spinors to covariant derivatives. Okay, so the question is, what exactly this covariant derivative has to be? Okay, so we have a relativistic 2+1 fermion. No, I'm setting the charge equals to 1. Then the covariant derivative will take this form. No? It will be the usual coupling to the gauge field. And then there is a coupling to the spin connection, where these J are the generators of the Lorentz transformations in 2+1 dimensions. And we're going to take the spin connection to be the Levi-Civita connection, okay, defined with the usual Levi-Civita covariant derivative. Okay, this could be more general. I can add a term to the spin connection, which is not the Levi-Civita part, and that will introduce torsion. Okay, but for simplicity, we are not going to introduce that kind of torsion in this system. So a spin connection for us is going to be always Levi-Civita. Now, if we consider the breaking of the 2+1 Lorentz symmetry to 1+1 Lorentz symmetry, then the generators decompose in this way. So we have this K generator, which is transverse to the anisotropic direction. So essentially, this is going to leave the vector L invariant. And there are these other two generators that will change the vector L if you do this transformation. Now, the spin connection decomposes in the same way. You have the purely transverse part to L and the rest. So we call them this omega mu and this theta mu. Now, if we look at the term in the covariant derivative involving the spin connection, it just splits in two parts. One part is just the coupling of this transverse Lorentz transformation with the transfer part of the spin connection, and the other part doesn't involve any of these two. Okay, so it completely splits this term in the 1+1 Lorentz transformation that will correspond to this piece, and the other transfer transformations. So we can see this omega mu as the gauge field for the SO1,1 Lorentz symmetry. Okay, and Newton-Cartan is quite similar, except that this spin connection is for space rotations. It will be an SO2S spin connection. So the term I showed you before that gives you the Hall viscosity, this Wensi term, if you use this spin connection, it doesn't give a Hall viscosity, just because it's involving, instead of rotations, Lorentz transformations. Okay, so you're not going to have any Hall viscosity contribution directly from this spin connection. Okay, so this is one difference with the Newton-Cartan. Now, this is just a rewriting of this term. If you are breaking the symmetry, this means that the relative coefficient of these two terms doesn't have to be the same. So you can have an arbitrary relative coefficient between the SO1,1 part, the 1 + 1 dimensional Lorentz transformations, and this other part. Okay, or you can rewrite this in a relativistic, in a 2 + 1 relativistic way with an extra piece here, with a different coefficient. So this will be the most general form of the covariant derivative. Now, this coefficient is not determined by the symmetries. No? This, you will need some particular specific model if you want to determine what this coefficient is. But this is not going to be relevant for what we are going to see, because we are interested in looking at what kind of terms you have in the effective action, but we are not interested so much in the value of the coefficients of this effective action. So the values of the coefficients are going to depend on alpha, but the terms you have are, they don't care what is the value of alpha, no? Just the coefficient in front of it. So this was just to determine what kind of combinations of background sources we can have in the anisotropic theory. Okay, so let me just write the fully covariant action. It will take this form. We have the projectors as before, the gamma matrices, and then we have to introduce the Welians and the covariant derivatives. No? So they appear whenever we have derivatives. Okay, so this is just the fully covariant form. Now, if we integrate out the fermions, we say we will have this partition function as a function of the background sources, including L. And the exponent give us the generating functional. So if we do a variation of the generating functional with respect to the sources, we can read from the coefficient of these variations, the stress tensor if we vary the Welians, or the current if we vary the gauge field. Okay. And then a second variation of these quantities will give us the correlators, the 2-point functions. We can apply Kubo formulas to that and extract transport coefficients. Okay, so this is the usual procedure to find these transport coefficients. Now, in the presence of the magnetic field, we have a gap. So this generating functional can be written as a local functional, completely covariant. No, this means in particular, it is invariant under diffeomorphism. In addition, we have two local symmetries. One is this SO1,1. No, the gauge field for that symmetry was this spin connection omega mu. And we have the U1, which has a gauge field A mu. And then we have to take care of writing only terms that have the PT symmetry. Okay, we allow breaking of P and T, but not PT. Now is where we are going to use this piece of information about how the Landau levels look in this semi-dirac semimetal. So we are going to do a derivative expansion of the generating functional. We are going to introduce a small parameter epsilon, which is essentially telling us the order in derivatives, okay? But not all derivatives scale in the same way. So in this lattice calculation, what we see is that the energy or the frequency should be of the same order as the momentum in the x direction, but this will be of the order of the momentum in the y direction squared. So we define epsilon using the momentum in the y direction, and then momentum in the x and energy go like epsilon squared. So now let's look at the background fields we have. So we're going to take that L, which is let's say, the coupling that is breaking the symmetry. This is going to be order 1 or order 0 in the derivative expansion. And also the geometry is going to be of the same order. Now, derivatives in the anisotropic direction, that's like Py, are going to be order epsilon. And derivatives in the transverse direction will be like Px or omega, so they will be order epsilon square. And now there comes some complication because we want to have a background magnetic field. So the magnetic field should be order 1. No? And taking this scaling of derivatives, this means that the transverse projection of the gauge field in a space direction should go like 1 over epsilon. But if we were going to make the time component of the same order, that will give you an electric field, which is order 1 as well. And we don't want that. We want the electric field to be small. So we are going to impose a different order in the derivative expansion for the time component of this gauge potential. Okay, so this breaks the scaling between these two terms, that was maintained for the derivatives. And then this part, which is just the gauge field in the anisotropic direction, can be order 1 as well. Okay, so this is going to be the complication, the different scaling between these two. Now, a comment is that in principle, the effective action written in terms in covariant form with all these background fields is insensitive on how we broke the isotropy. Okay, so if we have other systems that break the isotropy in a similar way, they will have a similar form for the effective action. However, when we do this derivative expansion, when we expand in epsilon, we are introducing an additional physical information that is this scaling. Okay, and that kind of derivative expansion, the dominant terms are going to depend on the system you're looking at. Okay, so what I'm going to say now is it will apply to something that has this particular scaling. So in particular for the semi-dirac semi-metal. Now, so one reflection of what I just said is that if you look, for instance, to this component of the electromagnetic field, this in the covariant action appears as a single factor. But when you decompose it in according to the derivative expansion, it contains multiple contributions in the derivative expansion. Okay, so in order to decide whether one term is of some order in the effective action, we just pick the lowest order. No? So in this case, that will be order epsilon to the 0. Okay, so we do that with all the terms in the effective action, and then we do the expansion up to the desired order. Okay, so let me introduce a bit of convenient notation. So we will define some curvature invariants using the gauge fields. The U1 has this F mu, which is just the field strength. The Lorentz spin connection has this curvature term. It's an abelian field as well. And with the L mu vector, that remember is like a Vielbein contracted with the vector L, we define this curvature, which is like a torsion. Okay. So this is the only type of torsion we are introducing in the system that is just allowed by the breaking of the isotropy. Okay, so in addition of this, if you want abelian curvatures, we can also construct a metric and find the Riemann tensor of that metric and use that to construct covariant terms. Now, with these curvatures, we can form several combinations, which are either scalar, like this one, or vector combinations with epsilon or without epsilon. So all these combinations involve the vector L in some way. So these are combinations that only appear once you have broken the isotropy. And we can contract the vectors to form new scalars as well. So these are the basic building blocks of the effective action. Now, at order epsilon to the 0, we have 3 possible vectors, which I collectively call u mu. One of them is L mu. And the other two, this V mu is essentially like the velocity in the whole, in the quantum Hall system. So it will be transverse to the electric field, but it has an additional L in it. Okay, so it's transverse to the electric field and to the anisotropic direction. And this J will point in the direction of the electric field, but transverse to the anisotropic direction. So with these vector fields, you can construct these Euler currents that I mentioned contribute to the whole viscosity if you have a relativistic system. And you can substitute any of these U's but by any of these vectors, but it turns out that there are only 3 independent combinations. So with these Euler currents, we will construct terms in the effective action, just contracting with the gauge field.
Sorry,
Yeah.
you are taking an expansion, low energy expansion effective action with denominators. What would you have something to do with the denominator there?
Yeah, this denominator is proportional to the magnetic field. Because the magnetic field is order 1,
Okay.
then it can appear, any function of the magnetic field can appear in the effective action. So this is to normalize these vectors to plus or minus 1, this denominator.
So the denominator is not a dynamical field, okay?
Sorry?
The denominator is not a dynamical field.
It has dynamical fields, but because there is a background magnetic field, it's never 0, because you expand around a background magnetic field.
Okay, so you could expand the denominator.
Yes, and in fact, we expand the denominator when we want to compute the response.
Okay, thank you.
Okay, so let me show just the order 0 terms, because there are just 2 of them. So this part here is similar what you have in the usual quantum Hall effect. You have the energy density, which is a function of the magnetic field. The difference here is that you have 2 scalar combinations. So you have like 2 magnetic fields if you want. And then you have the usual Chern-Simons term for the gauge field. So it turns out that this is the only contribution to the DC Hall conductivity. So this Hall conductivity is just determined by this Chern-Simons term, as it was in the usual quantum Hall. Now, for the Hall viscosity, there are 3 terms that can contribute. One appears at order epsilon and the other at order epsilon squared. So the order epsilon term looks like a Chern-Simons for this F vector that, if you remember, is the field strength contracted with the vector L mu. Okay, and then it has some coefficient C5, which can be an arbitrary function of these magnetic fields I show you. At order epsilon squared, we have a contribution which is like the relativistic Wensi term, except this V now has this L dependence as well. And you have this other term, which looks like a Chern-Simons terms for this L mu. Okay, so if you're familiar with the torsional Hall viscosity, this is similar to a torsional Hall viscosity term, except it only involves this L mu vector. So it only involves the spin connection projected in the L direction. It's not the full torsional Hall viscosity term. And it has this other coefficient F11. So as you see, in order for this term to be gauge invariant, kappa has to be a constant, but there is no such constraint on C5 or F11. They are already gauge invariant, so they can be arbitrary functions. Now, we compute the Hall viscosity using the Kubo formula for the stress tensor correlator. No, it satisfies this odd property of exchanging the first pair of indices with the second pair. And we find 3 independent contributions that we label isotropic, nematic, and vertical contributions. Now, each of these contributions is characterized by a different tensor structure that I call these P's with labels. And they take this form. Okay, so the isotropic one is just the usual Hall viscosity that you construct with the epsilon tensor and the dirac and the Kronecker delta. The nematic contribution has one component in the anisotropic direction and one component transverse to it, and is symmetric in the first two indices. And the vertical contribution is similar, but is antisymmetric. Okay, so because we have this rotational, this breaking of rotational invariance, you can have this antisymmetric contribution as well. So if we didn't have PT, there will be another possible tensor structure that will be allowed. That is simply having the projector in the both pointing in the anisotropic direction, both indices I and J. Okay, but this is forbidden by PT symmetry. Okay, so there is no term in the effective action that can produce this thing. Now, if we look at what are the values of these coefficients in terms of the coefficients of the effective action, you find these combinations. You see that in principle, you can extract, if you measure this eta iso, eta nem, and eta bor, you can extract the coefficients of the effective action, no? Because they appear in linearly independent combinations. If you are at the quantum critical point, if delta is equal to 0, you should have this scaling symmetry. And if you look at the scaling properties in the effective action, you see that this C5 should go like 1 over the magnetic field, and F11 should go like the magnetic field. So if you plug this in these expressions, you see that all the three contributions are linear in the magnetic field at the quantum critical point. Okay, and then as you change delta, there can be deviations that depend on B over delta. Okay, so these two coefficients were computed by my collaborators using some very curvature calculation. But they assumed that they had symmetric stress tensors, so they didn't compute this coefficient. So this so far has not been computed, this vertical one. Now, as I said, this kappa has to be constant to have gauge invariance. So we can think of this as a topological term. And then in the ordinary quantum Hall is determined by this shift, no, that you can compute if you put the fermions on a sphere. Now, for the quantum critical point, I'm not completely sure if, how it was computed. I mean, it was computed using these very phases, but the shift has not been computed and compared to the Hall viscosity. No? Okay, so let me finish here. So as we saw, the Hall conductivity is insensitive to this breaking of rotational invariance. It's going to be the same in the quantum critical point, even if we don't have isotropy. The Hall viscosity is sensitive, but if we take this combination of the isotropic contribution and the nematic contribution, this is just proportional to the topological contribution. Okay, so in principle, you can find a combination which is insensitive to the breaking of rotational invariance. Now, well, I comment several times that we have this particular scaling with the magnetic field close to this semi-dirac point. So if this was measured, that will be a smoking gun that you're really having this quantum critical point. And then future directions one can try to follow is try to compute basic contributions. So this is going to be much more complicated because, for instance, this Lorentzian spin connection is going to contribute to this AC transport. Okay, doesn't contribute to the DC transport of the Hall viscosity, but it will contribute to the AC transport. No? Along these lines, one can also try to find what is the dependence with momentum. See if there are some relations between different transport coefficients as it happens in the quantum Hall system. And then try to generalize this to other topological states which are anisotropic, no? Especially if there is a PT symmetry or something analogous to that, then you can use that to constrain the transport coefficients. So it will be interesting to see if these other anisotropic systems exhibit similar symmetries as well. And I will finish here. Thank you for listening.
Questions?
So I may have missed it if you said it at some point, but you started off with a right? So something that's quadratic in the fermions, right?
Yeah.
So why do you need to do it?
You mean why I don't integrate the fermions and find the effective action?
Sorry?
You're saying take the fermionic action and integrate out the fermions.
Yeah, like why can't you do it directly on the lattice and get all of this instead of trying to fix symmetries and so on?
Well, because this is simpler than here. I just construct the invariants, and these are the terms that can appear in the effective action.
Sure, but is there a fundamental difficulty with doing it the microscopic way?
No, there
shouldn't be, right?
fundamental.
So you could fix all your
difference.
coefficients as well and everything, right? If you wanted to.
We will be fixing all the coefficients for that particular system. It might happen that some coefficients that you could have according to symmetries are zero as well.
Sure.
So
If you don't include an interaction, that's fine.
yeah, I didn't include interactions in the effective fermionic description, but if the symmetries are the same, the effective action will be the same.
Right.
So you have this Chern-Simon term for F mu, right? That F mu is the dual of the field strength, right?
This F.
Yeah, the first one. I'm trying to understand, why it's connected to the whole viscosity. So is this is actually an higher derivative? So it's not topological, right?
Yeah, it is connected because no, this is the definition of F with X alpha mu being F alpha mu.
Okay.
So it has this L, and this L contains
it's
VL
inside
bind.
there. Okay. Okay.
So because there is,
Yeah.
it depends on the metric through the VL bind, then that gives you contributions to the stress tensor.
Okay. Okay. Then that's why the coefficient is dimension full in front of it. It's not like dimensionless like standard Chern-Simons, right?
That's right.
Okay.
Yeah.
Thank you.
More questions? Okay, we thank the speaker again and close the session.
Thank you.